Transport Layer Security, or TLS, is possibly the most common security technology in use today. There's a lot to say about it, but in this video we're going to look at the role X509 certificates play in the protocol. In a previous video, I discussed asymmetric cryptography, public-private key pairs, and X509 certificates. If you're not familiar with all these topics, you should watch that video first. If you're already up to speed, then here is SSL, TLS, and certificates from the beginning.
Let's start at the very beginning.
Stop that! You're not going into a song while I'm here.
When you talk about connecting to something on the internet, you're almost always talking about establishing a socket connection using TCP/IP protocol. A server will listen on a particular socket number. A client, that would be your computer, requests a connection to that socket on the server. The server accepts the connection, after which the client and server can exchange data in both directions until either the client or the server drops the connection. I don't want to spend too much time on TCP/IP, but I do need to mention where it falls into the Open Systems Interconnect network layer model developed by the International Standards Organization. This is the OSI from ISO. The model allows network traffic to be understood at different levels, from the physical technology used to transfer the bits to the application messages that these bits represent. The TCP part of TCP/IP is considered Layer 4, or Transport Layer. Layer 4 appears to be a seamless conduit of data between the client and the server. Details like traversing different kinds of networks, say from wireless to fiber, and the associated protocol changes are all hidden scaffolding at Layer 4. So when we think about exchanging data between a client program and a server program, we're really thinking about the data that's exchanged at the OSI model Layer 4. The data sent over a TCP/IP socket connection is not encrypted. If a third party can intercept the data packets and decode Layer 4, they can see all the data flowing between the client and server. That would include passwords, account numbers, and other sensitive data that's important to keep private. In the OSI model, application functionality occurs at layers 5, 6, and 7. If layers 1 through 4 are insecure, the system can implement security at one of the higher layers. Web browsers interact with web servers using the Hypertext Transport Protocol, or HTTP. HTTP doesn't maintain session state, Layer 5, but it does allow browsers and servers to negotiate content encoding, Layer 6. HTTP itself is at Layer 7, and here is where the web would most obviously add security. This was actually done with a protocol named Secure Hypertext Transport Protocol, or SHTTP. If you're thinking, did you say SHTTP? Don't we call it HTTPS? Yes, I said SHTTP. HTTPS is a different thing, and we'll get to it. SHTTP was a complicated enhancement to HTTP. It had, for example, the ability to encrypt selected parts of the data. It could encrypt and sign different parts of a request or a response with different keys. A design goal of SHTTP was that it would interact gracefully with plain HTTP counterparts. So if your browser didn't understand an encrypted part, you were supposed to just see that part redacted. In reality, it would just confuse regular HTTP browsers at a time when browsers were frequently having problems understanding regular web content. This was introduced at a time when the browser wars were introducing instability to the HTTP protocol itself. The SHTTP protocol and attempts to implement it made compatibility issues worse. On top of that, no one was asking for it. The primary reason no one was all that interested in SHTTP was that a much simpler solution to securing HTTP traffic already existed: Secure Sockets Layer, known as SSL. SSL puts an encrypted wrapper on the data sent over the TCP socket. The application then sends its unencrypted data securely wrapped by SSL. One of the benefits of this approach is that the application protocol, such as HTTP, doesn't change when it's being sent over SSL. This means that you get security without changing the underlying protocol and risking interoperability. So why did anyone go to the effort of formulating SHTTP? Keep in mind that SSL was created by Netscape, the first commercial browser company. They permitted other vendors, such as Microsoft and IBM, to implement it, but the technical specification of SSL was controlled by Netscape. Also keep in mind those browser wars that I mentioned before. It was a big risk for the future of the World Wide Web for a single company to control the way that web browsing was secured. SHTTP, for all its misguided complexity, was created as an open standard that wasn't controlled by a single for-profit company. But Netscape had already discovered that making their proprietary standard into an open standard was sometimes the best way to protect it. As Microsoft's JScript fought for supremacy over Netscape's JavaScript, Netscape did an end run around Microsoft by turning JavaScript over to the European Computer Manufacturers Association, ECMA, who standardized it as ECMAScript. As a result, JavaScript grew to be one of the most widely used languages in the world. Thus, it was an easy decision to make SSL an open standard, and in 1999, it began its new life as TLS. Because SSL operated at OSI Layer 4, it was renamed Transport Layer Security, TLS. I'll use SSL to refer to the early protocol that was developed by Netscape, and TLS to refer to the modern standard in use today. The adoption of SSL as TLS was a knockout blow to SHTTP. There was a reference implementation and a handful of products, but nobody is keeping the SHTTP flame alive. It disappeared, never to be spoken of again, except in historical retrospectives like this, and for some reason the CISSP exam. If SHTTP did anything right, it added security to HTTP. That's great, but SSL and TLS could add security to any protocol over a TCP socket. When an insecure protocol is sent over TLS, the convention is to add an S to the end of the protocol abbreviation. So that's where we get HTTPS. I told you I'd get to it. Okay, let's pretend we're Netscape, and we want to create a way for web browsers to communicate securely with web servers. We already have a way to communicate by using a TCP socket. Now we're going to create a secure socket that wraps the communication in encryption. How do we do that? The first problem is establishing an encrypted connection between a browser and a server that it may be contacting for the first time. As I explained in the previous video, we can initiate a secure messaging exchange using asymmetric cryptography. When the browser connects to the web server, the server will send the browser its public key. That allows the browser to send an encrypted message that only the server can decrypt. But we need the server to be able to send encrypted data back. We could just send the server our public key, but we neither need to nor would we want to. Asymmetric encryption operations are very compute intensive. Here's the encryption and decryption functions for the RSA algorithm. M is your data as interpreted as a giant integer. E, D, and N are also giant integers. When I say giant, I mean on the order of 2048 bits. At that scale, these calculations could take a second or more on late 90s computer hardware. The maximum message size would be 2048 bits, which is only 256 bytes. That's 256 bytes per second, and that's extremely slow, even by late 90s dial-up standards. What the browser should encrypt and send to the server is a bulk encryption key. The client picks a symmetric key, then uses the public key to securely send it to the server. Now this key can be used to encrypt and decrypt data at the same speeds it can be sent over the network. This is referred to as line speed. And it was faster than 256 bytes a second, even in the late 90s. Now we've solved the problem, and we only need one public key, the one from the server. It doesn't even have to be any particular public key. It could be one from a key pair that the server creates just for this one interaction. This is called an ephemeral key pair. With this one piece of data, we're able to securely exchange a key for a fast, efficient cipher, and now we can securely exchange data. Now I can send them my credit card info, right? No. I discussed the reasons why this is not really secure in my last video, but to recap, we don't have any confidence that we're talking to the site we think we're talking to. Even if we are ultimately communicating with the intended site, we don't know if there's a man in the middle snooping on our data. We haven't solved web security, but we have managed to invent SSL version 1.0, or something like it. SSL 1.0 was never released, mainly because it had the same security issues that our hypothetical simple protocol has. Here are some screenshots of early 1994 versions of Netscape, and you can see it prominently advertises the use of encryption from RSA. RSA is a prominent cybersecurity company, but it's also the name of the asymmetric key algorithm that's still one of its greatest hits. Unfortunately, while RSA is a great algorithm, it doesn't guarantee security unless you can verify the ownership of a particular public key. In 1995, Netscape released SSL 2.0 to the public. 2.0 fixes a lot of what's wrong with SSL 1.0. The biggest change was the addition of a mechanism for verifying the origin of a public key, the X509 digital certificate. As explained in the previous video, the X509 certificate pairs a public key with an identity, and the pairing is certified by a certification authority, or CA. A user can obtain the certificate of a trusted CA and use it to verify the certificate presented by a server it's connecting to. Every browser would come preloaded with a set of root certificates from a set of trusted CAs. When a web server presents its certificate, the browser verifies the signature of the CA that signed it. If the signature is not valid, or if the browser doesn't even know that CA, the certificate is not trusted. In addition, the certificate's expiration date should be checked. Even if the certificate is unexpired, it might have been revoked, so CAs published a certificate revocation list, CRL, that clients would need to download on a regular basis. If any of these verifications failed, the user is warned that the connection is not secure. Now that we know we have a valid certificate, does it match the website we're connecting to? The first thing that you know for sure is that you're communicating with someone in possession of the private key associated with the certificate. This is verified by an initial cryptographic handshake. But is the website represented by the certificate the website you're actually talking to? Let's back up a little. When you ask your browser to go to a URL, there's a name for that server, like www.amazon.com. This name is sent to the domain name system, DNS, to get an IP address. But what if that address is wrong? What if the website associated with that DNS has moved? It's not a simple question. Look at this DNS lookup and notice that the server answering at www.amazon.com is actually owned by cloudfront.net. But that doesn't matter. What matters is that the X509 certificate belongs to the site you are trying to connect to. To verify this, you can check the name of the identity in the X509 certificate and see that it matches the DNS name that you used to initiate the request. At the very least, the common name attribute in the identity needs to match the DNS name. In order to allow the same certificate to be used for www.google.com and search.google.com and just google.com, the common name can start with a wildcard, so it can be star.google.com. Additionally, a year after SSL 2.0 debuted, the X509 standard added the subject alternate name attribute, allowing for even more options. This Google certificate not only matches google.com, but a number of other Google DNS names as well. Bottom line, whatever match you use, there should be a name match between what you specified in the connection and what's in the certificate. While all of these checks were pretty effective, they weren't mandated by SSL 2.0. As a result, applications that used SSL 2.0 did not always perform verification properly, and that included Netscape's own browser. SSL 3.0 codified the checks needed to verify a certificate, leading to greater confidence in the trust model. It also provided support for trust chains by requiring the server to provide the site certificate and any intermediate certificates in the chain. The root certificate was still required to be installed on the client. Eventually, in 1999, SSL was codified as an open standard. Its name was changed from Secure Sockets Layer to Transport Layer Security as a reference to it operating at the transport layer of the OSI network model. TLS 1.0 mandated more validity checks, and even more were added in TLS 1.2 and 1.3, which is the current version of the protocol at this time. So, all of this verification logic was built into the SSL 3.0 stack 30 years ago in 1996. Since then, it has provided web users with enough confidence in the identity of websites that web shoppers now make over $6 trillion in transactions globally. Unfortunately, there are billions of dollars in losses as well, thanks to the fact that from the perspective of the web server, web users are anonymous. Even when they have to log into a site, that site usually doesn't know their real identity. This means that bad actors can connect to servers and perform malicious actions, and we might not have any idea who they are, especially if they're using credentials stolen from a legitimate user. It turns out that SSL, particularly SSL 3.0 and later, also allows for clients to identify themselves with a client certificate, solving the anonymity issue. This might not be desirable on many websites, but financial sites could benefit enormously from this mutual authentication and trust. In fact, financial service companies are by law required to know who they're doing business with. But banks don't use this feature of TLS. Typically, only high security organizations like the U.S. Department of Defense use client certificates to authenticate users on their network. This is an image of a DoD Common Access Card, or CAC. The chip you see in the picture actually contains X509 certificates used to authenticate the user to the DoD network. So why don't more organizations use this as well? Mainly because it's different enough from other forms of authentication that it confuses people. Not the users. It's actually super easy for the users. It's the implementers who can't seem to get it. This means that a lot of people think it's harder to implement than it actually is, so they avoid it. More importantly, users would need to obtain personal certificates that would be acceptable as a digital ID to a wide variety of organizations. There are places where you can get certificates that could fit this bill, but they're not free. Username and passwords are free. Getting the personal certificate requires going through an application process that can take several weeks. You can think of a username and password right on the spot. So, in terms of facilitating secure e-commerce, client certificates are just too much trouble. How much trouble? Well, there's enough to explain that it's going to be the topic of its own video. In the next video, I'm going to demystify client certificate implementations and explain why we're probably going to be seeing a lot more of them in the future than we have in the past.